All right, this is Ken Delcor here. I'd like to take a look at the specifically the 121 M1 13 PSI and water column. PowerPoint. And the intent of this and the idea of this is to try to get people to understand what the relationship between PSI and water column is. We have systems and we use this all the time where we'll say our PSI is, we might say a quarter PSI, a half PSI, 2 PSI, 1 PSI. How does that relate to water column? So I would like to start out this way and look at exactly what makes this up and how do we do this. So I think the first thing that I'd point out is that we're starting with water, and water has a density, and I'm just gonna say it has a standard density that we typically use. That standard density is actually about 62.4 pounds roughly at approximately 39 degrees Fahrenheit is the way that it is. That's standard density of water. Now, we know that can change. And so if water has a density of about 62.4 pounds per cubic foot, and so if we take a cubic foot of water, based on what we would know that this is true, if we take a 1 foot by 1 foot by 1 foot, so this is essentially 12 inches, this is 12 inches, and this is 12 inches. So we basically have this dimension, and this dimension. We simply made up a cubic foot of water. Now we put that on there, it's going to weigh 62.4 pounds on a scale, and that's going to be really what its force would end up being. Now, what if we, let's say we change that. Now, I want to go to the next one here, and we're going to talk specifically. So in that previous one, you'll notice how, excuse me, how we were breaking down this little cube. Obviously, to make a cubic foot of water, you have to have a lot of cubic of inches. And for example, if this is an inch, that means that there's 12 of them. 12 of them that way. There's 12 of them that way. And there would be 12 of them on the bottom there as well. So that's really kind of the point that we're going to make here. So let's go ahead and hit the next one up here. All right, so now this little 1 inch cube that we're dealing with on here. Now what I want to do to some extent, there's a little bit of the background here that isn't shown here, but I'm going to show this here. And there's also a handout that that's not bad to look at, but it might be a little confusing to some of you. So I'm just going to try to see if I can clarify some of this. So in the previous slide, notice how we had a cubic foot and we had 62.4 pounds. So what I want to do is what are we coming up with here? So here I just put that 1 cubic inch, and notice how the pressure went up to 0.036. Now how do we get that? So I'm gonna define that or clarify a little bit here to some extent if this will work. So if I take the 62.4 pounds, excuse me, for the water, pounds PSI, or pounds of water, and I divide that by, on that previous one, that was comprised of 1,728 cubic inches. So that essentially was 12 inches by 12 inches by another 12 inches. And we basically, that right there combined equals the 1728. So now when I take 1728 and divide that into the 62.4, what we end up getting is approximately about 0.036, comes out to like 0.036111 and so on pounds is what we end up getting. Thus, That's where that number is coming from. So that means the pounds per square inch is what that ends up being. So here you might notice, though, what might be a little confusing here is the fact that we're showing a scale here, or what we have on the scale is essentially 1 cubic foot. So if we think about that, the 1 cube that we're dealing with and to some extent that means we're simply looking at a 1 inch by 1 inch by 1 inch cube. So we've got, that's essentially a cube. So if you find 3 dimensions, that's what we're dealing with. So and the fact of the matter is this column of water is essentially 1 inch high, and it's a 1 by 1 square. So it's 1 square inch is what it ends up being. But the force in this case is 0.036 pounds. So that's kind of where we're getting that number. So whoops. There we go. All right, now in the next one here, what I want to hit up on a little bit here is, now remember earlier we had that 0.036. Now what I want to do is stack that up 7 inches high. So what I'm going to do is I'm going to keep stacking more and more of this up on here. So if we think about that every one of these is 1 inch. So there's 1, 2, 3, 4, 5, 6, and 7. Every one of those is one more stacked on top. So if you think about it, think of those as, having each of them having a weight of 0.036. So if we take 7 and we take that times the 0.036, that comes out to roughly about 0.25, let's call it, pounds of weight is what it is. Now remember, every one of those cubes is occupying that area that's essentially going to be 1 square inch. So to some extent, the 7 inches of water column, to some extent, we would have to say is going to be 0.25, let's call it pounds per square inch, which is also equal to 0.25 PSI to some extent. So we're looking at roughly about 1/4 of a PSI to some extent on this. So 0.25 pounds, 1/4 PSI. All right, so now let's go to the next one. And on the next one, what we've got here is essentially a column of water that's 14 inches. Now, if the previous one we had 0.25 pounds when we stacked 7 of those on there, and you could see how we figured that out, the next one would have to be 14 inches. So we're doubling the weight of the 1/4, which would now put me at about 0.5 pounds of pressure on there. So all those cubes stacked up on there give me a weight or a pressure of essentially 0.5 PSI. Now, this typically, the significance of why we're going through this is this 14 inches of water column is typically, I'm just going to make a note of that, that's typically the max pressure, that's typically the max pressure to most equipment. That's really what that means. So it's typically the max pressure to most equipment. So if you look at most furnaces, they might say 0.5 PSI, which is what that is. Or they might say 14 inches of water column or 13.6. And you get what they're getting at. That's what they're trying to associate that with that. And that's kind of how they're doing that. On the previous one, this 7 inches is if you recall from the other lecture, that 7 inches essentially is what I would say is probably the normal gas supply from a natural gas meter. So in our heating labs, let's say, for example, in the BC 105 lab, all of that equipment there would get roughly about 7 inches of water column, assuming there would be a gas meter that would be feeding each of those. And that's primarily the normal gas supply pressure that most of the systems are typically associating with. So, all right. So the next one that we're going to take a look at is looking at a column of water that's 28 inches high. Now, the 28 inches high, if we look at that, we're running into an actual full PSI, which makes sense. We've got at 14 inches, at 7 inches was a quarter PSI, at a half of a PSI was 14 inches. Well, certainly 28 inches roughly would have to be close to a pound. So that would be the equivalent of saying 1 PSI is equivalent to approximately 28 inches. Now, these are all typical numbers that we throw around, but we have to have an understanding of that. You're going to have meters that are going to say, well, our max capacity is 26 inches of water column. And so if you're running a 2 PSI system, one would have to know that, hold it, this meter is not going to work for this. And I need to make sure that I recognize this, that it's important to understand that. So that's this pressure here of 28 is certainly higher than that. Now, I want to expand this just a tiny little bit, and it's not perfect, but I'm going to show it to you anyways. So 28 inches, and how do we equate that to 2.31 feet? So what I want to do is I'm going to show you this. And 28 inches, by the way, is a rounded number, so it's not a perfect number. It actually comes out to like 27.7 inches, but so we'll just say it's 28 inches. Now, so I'll do it this way. So 28 inches of water column is what we have. Well, how many inches would be in a foot? Well, I think most of us would say that every 1 foot, so we'll say 1 foot has 12 inches. So the 12 inches would cancel out. And if I take the 28 and I divide that by 12, it's going to come out to, in this case, it comes out to about 2.33. Now, as I'd said, that 28 is a rounded number. So the real number is actually closer to 2.7, 27.7 is the typical number that you normally run into. So the actual number is really about 27.7 inches of water column is really what it is. But for the sake of doing our normal heating stuff, we don't need to be quite that accurate for most of this stuff. I think we're using these as quick ratios, and just as the 2.31 is a rounded number, it's actually this number is closer to 2.307. It's much closer to those other numbers, but there again, these are rounded numbers that are more appropriate to use. And I want you to recognize that each one of these, this one and this one, is what we would associate as your PSI. And I think that's the value of this. So those are equating to those pressures. All right. On the next slide, this is a great opportunity. Again, another viewpoint of it. This particular monitor, or what I want you to see on here, this particular magnehelic gauge, every one of these things is exactly 1 inch apart. This is no different than a basic ruler. And we've got a clear tube. We've done this in the past where we actually took a piece of clear tubing. We just taped it directly to a ruler, put some water in it, and put a pressure on it. And you could literally see the column of water change as you would either apply pressure or remove pressure on it. So it works so pretty good. Here's another one of these, filling it up. We got it all zeroed out. Now, if I put a little bit of atmospheric pressure on it, and this is all open, you can see how everything is zero. So the pressures are the same. Now, this is an instrument that reads differential. Now, if I apply pressure, so let's say from a gas supply system, or I'm going to measure duct pressure as an example, it would apply pressure in this manner that would force that column of water down down essentially an inch. But you got to remember, the forces that it's working against is it has to push the column a difference of 2 inches. So we're always looking at the difference between the columns. So we displaced it up an inch and we displaced it down an inch. And the total was 2 inches. So this is really a good little image to kind of show really the reading and how to handle those systems on there. Very, very good. So that essentially is the end of that little, I guess, understanding of the differences and the relationship between PSI, or pounds per square inch, and water column. So that was it. Thank you.